So we're going to focus on alcohols now. The biggest thing to take away from this is that alcohols, there's a lot going on here, but all this is really saying is that alcohols, similar to water, can be weakly basic as well as weakly acidic, right? So they call us amphoteric. So alcohols they can act as a base, where they take a hydrogen, or they can act as an acid, where they give up a hydrogen, and all those things are possible. So kind of that we know the basics of alcohols, weak acids, weak bases. How do we actually make alcohols? That's what this chapter is really going to be about, is how we actually make these things. All right, so how do we make alcohols? We make alcohols from these things we use these really reactive reagents called Grignard or Organolithium reagents. And we're going to do a nucleophilic addition to a carbonyl group. So let's take a step back. So what matters here? We're going to make a Grignard. That's what this is, or these organolithiums. So what are they? They're very reactive. And why are they reactive? They're reactive because they're actually carbanions, so negatively charged carbons, right? And these are really nice because they actually form carbon-carbon bonds. Right? We're going to form some CC bonds with them. So how do we actually make the Grignard reagents? Because again, these are all leading us to ways to make alcohols. How do we make a Grignard reagent? So let's look here. So of all of these, we start with an alkyl halide. So all of these have carbons that are actually electrophilic. What we're going to do is we're going to turn that delta plus carbon into a delta minus, or even a carbanion type carbon. And we're going to do that with a metal. Because metals are not very electronegative, what's going to happen is this metal is going to insert into that bond. So let's draw out, see what this looks like. Let me zoom in a little bit here. How about that? So imagine this metal has some electrons. There's, of course, 2 electrons in that bond. We're going to use those radical single-headed fishhook arrows. What's going to happen, if I draw this out, excuse that, the bromine's there. The metal is now bonded to that carbon, right? They formed this bond with 2 electrons, and this bromine is now bonded to the magnesium, shown right here. There's the 4 electrons. But what has happened? Because a metal's a metal and not very electronegative, that makes this carbon a really good nucleophile, makes it a carbanion. And we can see that over and over again. As we go down here, it could be magnesium, or it could be lithium can do this. One important note, because these are so reactive, you'll notice the type of solvents that need to be used. They need to be polar aprotic. So polar aprotic solvents. Aprotic meaning no OHs or NHs or things like that. Right? We can't have those around because this carbanion is so reactive that if there's any OH or NH, it's going to act like a base and take that H or that H. So we can't have any of those around if we want to have it react and form a carbon-carbon bond. So you got to be very, very careful with those. So again, what have we done? We've taken an electrophile, we've made it a nucleophile. Right? These are called Grignard when it's a magnesium, and they're called organolithium when it's a lithium. And these are really important because what we're going to do now, again, what are we going to do? We're going to form a carbon-carbon bond, which is going to actually end up helping us make an alcohol. So what is this showing us here? This is just kind of restating what I said, that when a carbon is bonded to a magnesium, it's really almost like a negatively charged carbon, a carbanion. It's more like an ionic bond. It has some ionic bond character, same with a carbon bond to lithium. So really treat it like R- or C-. And so they're very reactive. They're essentially carbanions, so they're very strong bases. So also be worried about those protic solvents again. Carbon bond to a metal is going to be a carbanion, really a negatively charged carbon. It's going to be very reactive with both an electrophile, a carbon that's electrophilic, but also protons. So let's see how these can be used to actually make alcohols. All right, so we've talked a lot about the nucleophile, this carbanion. We know we want to form alcohols, so what are we going to use? What's going to be the electrophile? Right? So the electrophile that we're going to use here is actually carbonyl, C double bond O. The carbon of a carbonyl group is really electrophilic because it's double bond to oxygen. It's a polarized bond. Here's a resonance structure of it. Right? You can see that one resonance form would be the pi bond breaking. Again, we see that this carbon is electron deficient, so it's a really good electrophile. So that's what we're going to use to react with our nucleophile, these Grignard or organolithiums. So we're going to add into these carbonyls. All right, as I said before in the last slide, very eloquently, that we have now found an electrophile to pair with our Grignard, right? To pair with our Grignard. The carbon of the carbonyl group is electrophilic. When our negatively charged carbon reacts with it, we're going to go from sp2 hybridized to sp3. This is called, a special name, this is called the tetrahedral intermediate. Right? A tetrahedral intermediate. Right? So this is adding in, we make a tetrahedral intermediate. Once you make the tetrahedral intermediate, you always ask yourself this question. Ready? Do I have a leaving group? Do you have any good leaving groups? You have a carbon, and a carbon. Are carbons good leaving groups? Is C minus very stable? I think we just covered that. No. So now we have this alkoxide. So if we don't have a good leaving group, then what do? Then we want to try to protonate this, right? This O minus. Right? So this is a new nucleophile. We've balanced our charge. Nucleophile. What are we going to react this O minus with? We're going to react it with dilute acid, or H3O plus, or even water will work. And what's going to happen, if I do Cl, right? We're going to form our alcohol, right? We're going to form the alcohol. So the steps again, nucleophile adds in the carbanion, the carbon that's attached to the magnesium, the Grignard reagent, the negatively charged carbon, is going to react with the carbon of the carbonyl group, which is electrophilic. It's going to break the pi bond between the carbon and oxygen, form a tetrahedral intermediate, right? Because we've went to sp3 hybridized now. We've formed a new carbon-carbon bond, right? We ask ourselves, anytime we make a tetrahedral intermediate, do we have a good leaving group? Do we have a good leaving group here? Carbon, carbon, carbon? Nope. Right? A good leaving group is something that can stabilize a negative charge, probably something that's electronegative, or could do resonance. Don't have a good leaving group? Then I need to protonate this O minus. O minus is going to react with HCl, form the alcohol. This is a two-step process. This is a step one, stop, mechanism's done. Then you go to step two, new reaction, new mechanism. All right, so now that you can do this, let's just throw a bunch of reactions at you, right? But it's all the same thing. It's all the same mechanisms going on here, right? What's happening? You have a Grignard, same nucleophile, R minus or C minus, a carbanion, and we're going to react it with different types of carbonyl groups. Formaldehyde is the aldehyde with two H's. Just any aldehyde, right, has one H, or a ketone. Every time we do that, we get a different type of alcohol, though. Right? If we use formaldehyde, we get a primary alcohol, right? An alcohol that's bonded to a carbon with two hydrogens. If we react a Grignard with an aldehyde, right, what do we get? We get a secondary alcohol. If we react a Grignard with a ketone, what do we get? A tertiary alcohol. Same steps. Addition, right? Addition. You get the tetrahedral intermediate in all three. Do I have a good leaving group? Nope. Next step, protonation, primary, secondary, tertiary, depending on our starting materials. So how does this work? If I want a tertiary alcohol, you need to think to yourself, wait a second, how do I make tertiary alcohols? Well, one way is a ketone and a Grignard. That should pop in your head. That's what we're trying to think about, right? Think about the products. Another really cool thing as well, right? What if you want to make a carboxylic acid? You can react with carbon dioxide, CO, right? CO is like a carbon dioxide is like dicarbonyl, right? Same idea, except this carbon is sp hybridized. So you're going to go from here, add in, and you're going to make an sp2 atom here, right? And now you have this O minus, which is just like a carboxylic acid that's deprotonated. You protonate it, and you make a carboxylic acid. So it's another tool in your toolbox now. So you know how to make primary, secondary, tertiary, and carboxylic acids from Grignards or CO2. So this slide, some people like this, is just the words typed out of what I've kept saying, right? So if you need to read through this, that'll help you about all these steps. But so there that is, right? What's the nucleophile? What's the electrophile? Nucleophile is the Grignard. There's my electrophile. Tetrahedral intermediate. Do I have a good leaving group? No. Nucleophile, electrophile, right? Just all those steps. That's just written out here. What if you did have a good leaving group? That's next. So we know how to react with aldehydes, know how to react with ketones, and CO2. Now we're going to react with an ester. What's the first step? Addition. Nucleophile reacts with the electrophilic carbon of the carbonyl group. Break the CO pi bond. We get a tetrahedral intermediate. And what do we ask ourselves when we form a tetrahedral intermediate? Do I have a good leaving group? Do you here? You do now, right? You have an OR, an O minus leaving group, right? Oxygen is more electronegative than a carbon. It's okay as a leaving group, having a minus charge. So the electrons come down. Now we do an elimination. Instead of a protonation, now we do an elimination, right? So if this was an addition, this is an elimination reaction. And overall, what do we end up with? A substitution reaction, right? Remember your 4 reaction types? Addition, elimination, substitution, and rearrangements. So in this case, you do an addition. You have a good leaving group with a tetrahedral intermediate. You do the elimination. Net overall, what'd you do? You replace OR, the green OR here, with the red R1. That's a net, right? It's a net substitution overall, net or overall. All right? But be careful, because we're not done yet. Because what did we just make? We just made a ketone. Well, shoot. Ketones are pretty reactive, right? We just got done doing that. So if we make a ketone, is a ketone going to react with the Grignard or organolithium? Yeah. So this is actually going to keep reacting. So now we're down here. So notice here with this Grignard, you can't stop it. There's no way you can stop at the ketone. And notice there's 2 of them here. There's 2 equivalences. So another Grignard is going to come in and react with the ketone you just made, which is the same mechanism we saw before. Grignard adds into the carbon of the carbonyl group. That's electrophilic. We break the carbon-oxygen pi bond. All right, so this is, again, another addition. We make a tetrahedral intermediate. We ask ourselves what? Do I have any good leaving groups? Now do you have any good leaving groups? Carbons and hydrogens are not good leaving groups. So now you need to do what? Protonation or proton transfer. So protonation. And now what have we made? We've made a tertiary alcohol, but notice something. What is different about this? We added the same 2 groups, right? Unlike before where we only added 1 carbon group from the Grignard, with esters in Grignard, right, you're adding the same Grignard twice. So when you make that tertiary alcohol, you're going to have the 2 of the same groups off of that carbon. All of what I said in words written out, if you want to read it, just double check. We asked this before when we asked about solvent. There is an issue here. Because a carbanion is such a good nucleophile, it's also a very good base, right? Because all nucleophiles are bases. So if you have any sort of solvent around that has OH, NH, SH, pH, protic, right? Protic. Remember protic solvents? OH, SH, NH, pH. The Grignard is going to react with that first or as well. And that's going to ruin your reaction. So instead of forming, right, a carbon-carbon bond, right, if you want to, right, this is just going to react as a C minus with an H. And what do you get? All you get there is a new CH bond. So you got to be careful what solvents you choose or what else is around, right? So be careful of those protic solvents.